This is our 8th lecture, and I think it will be the first segment, the segment A of the 8th lecture. So let me begin with with few definitions that we may need later in this lecture. So we start with the following concepts. So let me write it down. I write a definition. And suppose X and D is a metric space. And B, which is contained in the power set of the sets X, is a family of all Borel sets. Borel sets in X. That means simply this is the smallest sigma algebra generated by the open sets in X. Smallest sigma algebra. 10. A measure space. And look, this will be X, and the sigma algebra will be exactly this sigma algebra of the Borel sets. Mu will be called, and let's just simply to indicate that this sigma algebra is the Borel sets, and we are dealing here with the metric space. We'll call it metric. Metric measure space. What is interesting about this metric measure case, we have here that, so let me maybe put it like this. Notice, that's after the definition, that for a metric measure space, and this will be X, and this will be Borel sets mu, and any measurable set, let's say A, we have the property that the measure of this set A can be written as infimum of all mu u, and here we have here A is contained in U, and U is open set. And you can also go from the other side, so this from the outside you can go supremum of the mu K, and here K is contained in A, and K is compact set. So we have these nice properties. We'll be referring to these properties in a moment. And let's put another one definition. Let X, and I put here mu, and here M and mu be a measure space. Then we will call it, and put here a finite measure space if, maybe change the color, if the measure of whole space is finite, and B sigma finite if first of all there exists, put it like a bullet, there exists a sequence x n which is contained in M with measurable sets satisfying okay, let me write it down. If there exists a sequence let's say xn contained in M satisfying a bullet lamp for every n the measure of xn n is finite, and the second bullet we have here that x is equal union n is equal 1 to infinity x n. Okay, so those are the definitions, and let's start with our first result. Let's start theorem. And let's write it. Let x m mu be a measure set, and assume that 1 is smaller than p smaller than infinity, then the space, and here we have L p x mu is reflexive. Yeah, very good. So that's the statement, and let's prove it quickly. And the proof will not cause us any problems because we are almost done, thanks to the previous theorem that we proved in the previous lectures. Namely, we showed that LP, but not for all p's, but only for p larger equal than 2, is uniformly continuous, so uniformly convex. So let's do it following. So first of all, notice that if 2 smaller equal than p smaller than infinity, then LPx mu is uniformly convex by our last lecture result. So by the Millman-Pettis theorem, in such a case, LPx mu is reflexive. Now we need to prove that for other p's it's also reflexive. So let's start to complete the proof. We consider the following map, actually operator. I do know this operator T. For a moment, we do not assume any assumption on the value of P. So for a moment, so 1 smaller than P smaller than infinity, we don't need it. We'll be referring to this operator in the next theorem, So we need to write it down in such a way that we can use it later. So that means x mu, and this will be star, where we have here 1 over p plus 1 over q is 1. So this means that this is kind of a p and q are related by this condition. So it's like a dual numbers, one to another. So, and we put it like this, Tf on the element from LQ, so call it G, will be equal, and I put here integral, and this is f g d mu. So remember, f belongs to the LP x mu, and g belongs to the LQ x and mu. So you see, so then, of course, so just realize, not we have to realize that this operator becomes an operator from LQX mu, so it's a continuous linear function on the space LQ, and we have, so we can just simply write it down, so this will be absolute value of Tf of G is equal absolute value, and I have here by the definition f g d mu, and now we can use the Holder inequality, and we are getting this is f is equal p, g is q. So we have here that this operator, okay, write it down, the norm of Tf, which is this operator, this linear function, as a linear function is smaller equal than f of p. But we claim that this is actually, so put it like this, we claim that actually this norm is equal to f of p. Indeed, consider the following function. So I can take the function, I put here like a g0 of x, and I define this function using this formula. So this will be like a f of x divided, and will be absolute value, and this will be f of x 2 minus p. And since, you know, I'm doing a division here, so 2 minus p, so I will assume that this is in the case that value is non-zero, and 0 I put here otherwise. So now let's compute the norm of it, but I will compute the q norm. So say it like this, and I put here q norm, take it to the power q first, so it is easier. So this will be basically nothing else than you take g0 and take it to the power q. What do I get here? I'm getting here, this is x, and then you are having here, I put here bracket, take the absolute value, do some simplification. So this will be f of x divided by 2 minus p. And now you have to take it to the power q, and then d mu of x. So let's continue. So you are getting here that this is x, and here I'm getting here f to the power f here of x, forgotten. So this will be cancellation, so this will be q divided by 1, not exactly, q divided by p minus 1. That's what we get, d mu. To be clear what those numbers are, write down the the relation 1p plus 1q is equal to 1, and we are getting that this will be equal 1 over q is equal p minus 1 over p. So we have here that this equivalent to p, maybe go to the next slide. So this is equivalent that p is equal q times p minus 1, which allows us to simplify this expression, and we are getting x, and then we have here f to the power p d mu, and this gives us f norm f p, and this will be p all. And that implies immediately, so we have that G naught belongs to the LQX mu, and we also know that the norm of this Q is equal to the norm of F P, and this will be P divided by Q, P divided by Q, which from the above relations it gives you immediately that this is p minus 1. Very good, very good. And now, and since if I take now TF and apply it to this G0, I'm getting here that this is X. Very good. And then I'm having here, this will be F squared divided by absolute value. Sorry for F squared divided by absolute value of F 2 minus P d mu, and that implies that this was equal to integral of x, which is F, to the power P d mu, and again you are getting here that this is equal F, and this will be P to the power P, which can be written like F P to the power 1, and this will be F P to the power P minus 1. And now you look here, that is exactly the norm of the G, so we are obtaining that this is equal to F P, and that one is G0, and I have here Q, and that therefore thus the norm of TF is larger equal than the norm of FP, and the conclusion follows. So what did we achieve? So we achieved that T is an isometrical operator, isometry that takes the space LP and put it inside to the space LQ X mu star, isometry. So that we have, and we can call it isometric embedding. And so we can identify the subspace L, which is equal to T of L P X mu, is the subspace of this space Q X mu star, with the space L P X mu. But now, if one P smaller than 2, then we have here that LQ X mu, since in this case Q is larger than 2, 1 over P plus 1 over Q is equal to 1. This space LQX mu is reflexive. On the other hand, we know that space is reflexive if and only if its dual is reflexive, so the dual is also reflexive. And since the dual is reflexive, then any closed subspace of that dual means any reflexive space, LQ of X mu star is reflexive. Yes, because closed subspace of a reflexive space is reflexive, and consequently L is reflexive, and which implies LP X mu is reflexive. And we finished the proof. That is the end of this proof. So let's go to next theorem, and this is kind of related to that one, and we'll simply write the next. This is important results. We will in certain way continue the construction that was here, and we made actually the observation. This theorem is called the Riesz Representation Theorem. And put it like this: for, okay, maybe we should say, let X M mu be a measure space, and now 1 smaller than P, smaller than infinity, an arbitrary number, and so maybe I just write it down like that, dot, then the operator, and I put here like this, T that we just considered in the other proof, so that means put it like this, P from X mu to LQ X mu dual, and I put here 1 over P plus 1 over Q is equal to 1, given by, and this will be TF on G is equal to integral F G d mu. F belongs to the LP X mu, and G belongs to the QX mu, is bijective. Satisfies that T of F is equal to the norm of F P. And what does it mean actually? That means, in particular, we obtain that that LQ X mu star actually is equal to LP X mu. So you can see that that's what we need to, that basically says that every functional, bounded functional on LQ can be represented by this integral formula, by the integral formula here. That's why it is called the Riesz Representation Theorem. And let me do the proof, which is kind of a simple and almost done. So proof. We only need to show that this space, that L, which is equal by the definition, this is T of L P, and this is X mu, that this subspace is equal to L Q X mu star, that is equal. But notice, since L is closed subspace, since this is closed subspace, it is sufficient to prove that L is dense in L, Q, X, mu, and that one. Okay, so let's do it. And for this purpose, suppose that, wait a minute, suppose that psi belongs to, take it to the second double, because it's something, because this is the double of that space, be such that, just simply that psi is orthogonal to the subspace L. That means simply that for every phi belonging to L, we have here that psi on phi is equal to 0. That's exactly the orthogonality property. But what does it mean that this is phi? Phi belongs to L if this is the image. So that means this is equivalent, that for every f belonging to the L px mu, we have here j, not j, we have here psi on t of f is equal to 0. But we just proved it by previous theorem, L, in our case LQ of x mu is reflexive. Therefore, any functional psi is equal to, so function psi is equal to, let's write it down, j of certain function g, for some function g belonging to L Q x mu. Yeah, because that's the second dual is the same as the original space, so we can write it down. So we have, and now we can write it down. For every f belonging to the LPX mu, we have here this one, so let's write it down. So I'm getting here 0 is equal j of g, and then this is t of f, but by the definition of the operator J, this is the same as T of F on G, which is, okay, this is X, and that means Fg d mu. So now, let me do the trick. So take the function G, take the function G, and now I will G of X define in the same way we were playing before, except this time, no. Let's take the function. For a function, I define the function f, will be exactly the same as we played with the function g, so it's going to be g of x, and this will be 2 minus q, if g of x is different than 0, and 0 if g of x is equal to 0, and we obtain, so we have that, first of all, the norm of f, and I put here like this, t is equal to the norm of the g q, and this will be q minus 1. Interesting. So, and we can rewrite it down. So, I don't have space, so let's go to the next one. So, if in this case, maybe we should be careful. Maybe I should write it down. I put here, call this one G naught, so you understand. This is a very specific element, such that it represents this functional. So this will be G naught, and this will be G naught. And f is constructed, so now I go to the next one, and here we have here 10. Let me write it down. Okay, so 10. We have here that this is 0 is equal, write it down. This is psi, and it is written on this f, on this particular f that we have it. So that was shown that this is the same as x, and this one is g naught times f. Maybe you're right. You have, yeah. It could be like this. Take f naught. Call this f naught also. So it will be like we will not understand that this is particular. Say it is in particular. So now you understand that this is particular for this particular f naught. So I put here f naught, and then continue, this will be equal d mu, and what do I get? I'm getting that this is the same as g0 q to the power q, and that implies that the norm of g0 q is equal to 0, so g0 is a 0 almost everywhere on x, because the norm is equal to 0, and psi, which is equal j of g0, is also 0. So that means we prove that any functional which is 0 on subspace L must be 0. And that implies, that concludes the proof of this theorem. So let me continue a little further, and let me do another, let's say, small proposition, or maybe call it proposition. Or proposition is good. And this will be just simply proof will be not just more sketchy than precise. I would prefer not to go into too many details, because the course is going to end next week, and I would like also to cover some basic facts about the Fredholm operators. I need to finish it quickly. So let me do the following. So let x D be a compact metric space, and consider the metric measure space, and this will be X, and this will be Borel sets mu 10 for any for all P such that 1 is inclusive, P is smaller than infinity, this space of continuous functions, maybe like this, the subspace of continuous functions on X with the values to R, maybe write it down, X, which is equal the set of all phi from X to R, phi continuous, is dense in LP X mu. So this is a dense subspace. In other words, every LP function, call this like f belonging to LPX mu, can be approximated in this space LPX mu by continuous functions. And the proof is kind of not difficult. So notice that simple measurable functions, simple measurable functions, let's call them clearly what it is. So you have here measurable sets, so you have here alpha, k, and then characteristic function of a certain measurable set an. So this is k is equal to 1 to n. So such function, linear combination of the characteristic functions of the measurable sets is a simple function. So this is equal 0 if x does not belong to A, 1 if x belongs to A. So this is a simple. This represents, so simple functions, approximate measurable functions. That's one of the main results that anyone should know from the real analysis. And in such a case, if you want to show that you can approximate LP functions by the continuous function, you can simply say this is sufficient to show that any characteristic function for measurable, A is of course measurable set, can be approximated by continuous function. So indeed, notice that we have here by the formulae. Let's go back. I'm going to use it now. So let's go to the beginning of the lecture. So we have this relation the measure of the any measurable set is actually the infimum of the open set, and this will be supremum of the compact set inside, and U is outside. Let's say contains A inside, and K is contained inside of A. So, in such a case, notice that for every epsilon larger than 0, there exists a U containing A, U is open, and there exists K containing in A, K is compact, such that the measure of U minus K is smaller than epsilon. And therefore, what should I say? I should say like this: put my function that will approximate the function, characteristic function of A, is just simply given by the formula. So let me write it down. This is distance between X and U complement. U complement is closed, so this is compact. Very good. And this is distance between X and K plus distance between X and U complement. And we can see clearly that this function is phi of X is equal to is equal to 1 if X belongs to K, and it's equal to 0 if X does not belong to U. And in such a case, since A is in between, we get immediately, and let me write it down, that phi minus characteristic function of A, and I put here P, let me make to the power P, because it will be easier. So this is equal, this is equal, so put it like this, this will be integral, and then you have here phi of X minus this one A of X, and then d mu X, and then since clearly you can see what happens here. So here, suppose this is my set U, and my set K is that one, K, and then the set A is that one, A. So the function, characteristic function of the set of this, so this will be 1. Characteristic function of this set looks like this. And our function, okay, our function looks like that. So this is characteristic, and then you go like it down and goes down. So you see these two functions are different. So the phi of X minus characteristic A of X not equal to 0 if X belongs to U minus A. Not necessarily. So this will imply, basically, that doesn't mean anything, just simply implies. So I can write it down. This one is smaller equal than integral of U minus A phi minus XA d mu, but that difference is always something in between 1, so that one is smaller equal to U minus A d mu, which is smaller than, let me go down, which is smaller equal than measure of U minus A, which is equal to epsilon, And then it's clear that in such a case, this phi minus psi A to the power P, the norm of this two function, is smaller equal than epsilon to the root P of epsilon. So clearly you can make it as small as possible, and the and in this case the conclusion follows. The conclusion follows. Maybe I should make a small remark. So let me put it like that. So let XD be a metric space, and phi belongs to, so maybe write it down like this. Phi is a function from X to R. Then we define the so-called support of the function of phi by the formula. So simply we write it down. Support SPP of phi is equal, and this is going to be, you take the set of all x's such that phi of x is not equal to 0, and you take the closure. And we also put the subspace, the C of x, to be a subspace. This defined it as the set of all phi belonging to the, so this is all functions phi from x to R, such that A, phi is continuous, and B, support of phi is compact. So that means this is the set of continuous functions with compact support. And maybe let me notice, let's say if this is compact support, any function on this is there. Yes. And so notice that for any phi belonging to CC of x, maybe I should not get into it. No, I don't know. Yeah, we'll talk about it in a moment. So let's say this is our definition. So maybe the idea is the following. So put it like a theorem. I will make this theorem only for Rn. So we claim, consider the space LP, and this will be Rn, and with mu, where mu is a Lebesgue measure on Rn. 10 CCRn is contained in CC is contained in LP Rn mu for any p, actually, for any p, for all p. So this is one smaller p, smaller equal than infinity, even for infinity, and CCRn is dense in LPRn mu for one smaller equal p, and strictly smaller than infinity So please pay attention here. The sketch of the proof is easy, so proof you will find out, so you take it is sufficient to show that for any measurable set A such that the measure of A is smaller than infinity, so that's set in Rn, we can approximate the characteristic function of this set by continuous functions from CCRn. And this can be done like this. So of course you can assume that this is your set A. This is just a sketch of the proof. And we know that Rn is sigma finite. So here we have here Xn. Those are the compact n balls of radius n, and clearly Rn in such a case will be union of these balls Xn. N is equals 0 to infinity, 1 to infinity. And then we can show that if you have here the measure of A is finite, so it's smaller than infinity, then you can show that for every epsilon larger than 0, there exists an n such that n, belonging to n, such that if I take the set A intersect with the set Xn, take the measure of it, so this measure, which is smaller than the, so maybe write it down like that, so this will be like this, measure, that the measure of A minus the measure of A intersection with Xn will be smaller, let's say, epsilon over 3. So that means here, we are getting here, maybe go back to the previous set. So I take this is my set A intersection Xn, and this is the remaining portion. That means that this remaining portion has the measure of this remaining portion is smaller than epsilon over 3. So this is epsilon over 3. So that remaining portion has a smaller. And now we know that if you take this ball, so this is my big ball of radius n, so it's a compact set. So now you have here the set A sitting there. So this is my set A. This is my set A intersection with Xn. And we know by the previous proposition there exists a function phi such that phi of x is, let's write it down, phi of x minus, and here we have here that guy, and I put here A intersection with Xn, and the norm, and this will be like, P is smaller than epsilon over 3, so such a function phi exists, and phi is continuous on Xn goes to 0, 1, that's how it was constructed. And now by the Riesz theorem you can extend this phi to the whole space Rn, so the extension exists, denoted by phi tilde, and once you have this extension, now you can find a small delta, little small delta, maybe like this, delta. A small delta, and you take the small delta neighborhood. So what is the small delta? So this delta is equal to, so positive number such that I put here like this, x and delta will be equal to xn plus, and I put here small delta 0. So that's a little neighborhood. So look, there is a little neighborhood here, little things here. This. You should understand that by the continuity of the measure, we can always, maybe black. One can always find delta small sufficiently small such that the measure of xn delta minus xn is smaller again. You can take it, we will say it like epsilon over 3 root of p, because we want to have it like everything is good. And then you have it. So now you define your approximation, your function that approximate, call it psi. The good one will be just simply take the horizon function, so put it like this, horizon function for this particular, okay, maybe like this, okay, so take the horizon function, so call this one eta from Rn to 0, 1, such that eta of x is equal 1 if x belongs to the xn, and 0 if x does not belong to the xn delta, and then your function, and the function, call this one psi, which will be equal to eta multiplied by phi tilde, is the required approximation of that one. So that's it. So this is the sketch of the theorem, and we do not have time for more details, but I hope this thing works, and you can check out the details later. So let me maybe stop here